Okay, what we're going to do today is we're going to go over a few static examples so you can do your practice problems and your assignments a bit easier. First problem we have is a concurrent coplanar problem, and that means that all of the forces are going back to the same point. That's concurrent. Coplanar means they're all within the same plane. What we need to do here is we need to figure out the tension in this rope, AB, and then the tension in the beam, AC. Okay, so what we need to do first is we have to resolve the forces. So any forces that are at angles need to be resolved. And that's going to make solving the problem so much easier. So anything that's at an angle, which TAB and FAC are, we're going to resolve them. Okay, so for the top, we're going to make a triangle. TAB is the hypotenuse. TABX is pointing to the left because this is pointing to the left. And then TABY is going to be pointing up. That's that side of the triangle because that is also pointing up. So when we do that, our forces, the TABX is going to be TAB sine 45 because it's opposite, okay? And then the TABY is going to be pointing up. TAB cosine 45 is because it's next to it. Now, if we look at the force on the bottom, we find that FAC, okay, we're going to make the triangle. FAC is the hypotenuse. FACX is the bottom pointing to the right, and FACY is upwards pointing towards A. So the forces here, FACX, are going to be FAC sine of 30 because it's opposite. And then FACY is going to be, that should be equals there, FAC cosine 30 because it's adjacent to the 30. Now, if we take a look at the 50 kilogram weight, it's already resolved, okay? But that's a mass, so we need to convert that to a weight. So we multiply that by the acceleration due to gravity, 9.8, and we get 491, okay? Now that we have that, we can go ahead and form our equilibrium equations. Basically, we write down everything that is in the x direction, add them to each other, and equal them to 0. Now this one is going in the negative direction, so that's why it has a minus. This one is going in the positive direction, that's why it's a plus. And we add them together, that should equal 0. We have three forces in the y direction. We have this one that's going straight up. We have this one that's going straight up. And then we have the weight that's going straight down. Okay, so we've got all this information. Now this looks really complicated. So what we are going to do is we are going to simplify these trigonometric functions and get rid of them. That way we can write them a little bit easier. Okay, and we have two equations and two unknowns. And this, what we're simplifying here, this is what we get. So if we take that sine 45, we get the 0.707 and it's negative. If we take the sine 30, we get the 0.5. Again, the cosine 45 is 0.707, and then we get the cosine 30, and then we have the 0.866. So there we go. All right. Now the next step is we're going to use simultaneous equations. When we add them together, okay, this is what the second, oh sorry, if we add both of those equations together that were on the previous slide, this is what we get. Okay, the TABs cancel out because one was negative and one was positive. So we get this nice value. If we simplify this, and we can get this value. So we get 1.366 FAC is equal to positive 491. So now we can just basically solve this, okay? And when we get a value of 359.4 newtons, okay? So we've got one of our answers already, okay? So we're going to take this number and we can substitute it either in the original FX or the original FY equations to get the value for TAB. So what I did is I used the FX equation, okay? This is the FX equation. What I did was instead of writing the FAC, I took this 359 and I put it in place there, okay? And then I can just basically simplify this and solve, and we get 254.2 newtons for TAB. Our next example is going to be a non-concurrent coplanar. So if we take a look at this one, we see that all of these are in the same plane, but they don't go back to the same point. So I've got this one force here that's at an angle. I'm going to have a force here at B, and I'm going to probably have a couple forces here at A. I'm also going to have this distributed force here. It basically means that it's equally distributed out between these 2 points. Okay? So the first thing we need to do is that angular force, we've got to resolve it. And then we're going to resolve the distributed force. Okay, the angular force at the end, this is a 5, 12, 13 triangle. It's a standard triangle. Since the size of the hypotenuse is 26, that's 2 times the 13 for the standard triangle size. So we just need to multiply the other sides by 2. Okay, so then we get our values. We get fx equals 5 times 2, which is 10, and fy is 12 times 2, which is 24. Now for the distributed force, we need to find the simplified load and location. So we need to take all of this, all these errors, simplify it into one, and then figure out where that's located. Now the simplified load is basically the area that is made by this rectangular shape. So the height is going to be 15 because that's the value of the force, and the width here is 2 meters because that's how wide it applies. So the simplified force is 15 times 2, and that's equal to 30. Okay, now the location is going to be exactly in the center. Okay, so that's going to be 1 meter from A or 1 meter from B. All right. The support A is a pin, so therefore we're going to have a force that goes in the upward direction and a force that goes in the horizontal direction. And support B only touches in one place, so it'll have one force there. Okay, so the new free body diagram, if I draw, and you should always do that. If you go back to the other slide, the free body diagram looks really complicated. We always simplify it here, that way we know what we have. So we've got this simplified load, we've got the resolved load over here, and then we've got our unknowns. So we've got 3 unknowns here. So now we can create the equilibrium equations that we need. Okay, here are the equilibrium equations. If I go backwards and look at the forces in the picture, you'll see that I have AX and 10 basically just looking or facing each other. For the Y, I have 2 of them, okay, AY and BY, and then I have the distributed force and the vertical force that's in the triangle. Now for my moments, I'm going to have to look at the force and the direction from A. So that 30, that simplified distributed force, is 1 meter from A. The BY is going to be 2 meters from A. Okay, and that 24 is 3 meters from A. So that's where my moment equation is. The easiest one to solve by looking at all these is this one. We have one variable. Let's go ahead and solve it, and that AX is 10. Okay, the next one that's easiest to solve is this moment equation. Okay, that's going to make, there's only one variable here, so that's going to make sure that's going to be easier to solve. The reason why AY and AX don't show up is because they pass through A. So they are actually there, but they say AY times 0 and AX times 0, and they cancel out. So by solving this equation with algebra, we get 51. Okay? Now the very last step is to substitute that information into that BY and into the FY equation, and we can solve for AY. When we substitute that in, we get AY equals 3.